Okay, this will be a quick video on position, velocity, and acceleration for a system of particles. So let's go through the setup. We have our inertial frame G. G means ground, and remember, inertial frame means that the frame is not accelerating and it is not rotating. That's what makes something an inertial frame. And that's EX, EY, EZ. And we have this point O, this orange point O, which is fixed in G. So that makes it an inertial point because it is fixed in the inertial frame. We have all these masses that are hanging out in space, and they're located with respect to our inertial point O with their position vectors. So mass 1 is located with vector r1, mass 2 is located with vector r2, and mass n would be located with vector rn. This purple vector, r with the overbar, this is the location of the center of mass, which is located at point C. And this funny symbol here is used to denote center of mass. So we're going to go ahead and define what the center of mass is. So the center of mass is defined as, it's either this position vector RC, the location of point C, or again, you write it with an overbar. Overbar means center of mass. And that's equal to, in the numerator, m1r1 plus m2r2 plus ... however many masses you have, all the way up to mn_rn. And then the denominator, you have the sum of all the masses, m1 plus m2 plus ... all the way up to mn. And if we just kind of look at this and think about it for a second, this is almost like you're assigning weights to each of the position vectors, right? So if m1 has a really, really high mass, that's going to put a lot of emphasis on r1. If m2 has a really, really big mass, r2 is going to, have a lot of influence on where the center of mass is. If we had some other mass, r3, and it had a little mass, a very small mass, it's not gonna influence or move the center of mass as much. And so if we look up here, if m1 was really, really big compared to m2 and the other masses, the position vector C, that's going to get pulled. This point is going to get pulled closer to m1 because it's having a greater influence on the location of the center of mass. So we can rewrite this numerator as, this summing notation, the sum from I equals 1 up to n of MIRI. That is exactly the same as this. And then in the denominator, we just have sum of all the masses. So from I to n, m sub I, sum of all those. We are just going to call this here, this sum of all the masses, we're just going to call that regular m, normal m. This m here is the sum of all the masses. And this stayed the same coming over. And so there we go. We have our final definition for the position vector of the center of mass. It is this right here. So, yep, I already said this, where m is the total mass of the system. So let's move on. Let's start developing the velocity of the center of mass. So the linear momentum, recall from a previous video, the linear momentum for a single particle is just the mass times the absolute velocity. And absolute velocity means it's with respect to an inertial point. So m times v, that is equal to p, which is linear momentum. And, if we want to find the total linear momentum for a system of particles, it's the same idea. We just add up all the linear momentums. The sum of all the linear momentums in the system is the linear momentum that's in the system. So m1v1 plus m2v2 plus mnvn, that can be written as this right here, mivi, from I equals 1 to n. That is the total linear momentum for a system of particles. So the derivative of position is velocity. So we can write this p that we just found as, same notation, mi, nothing changed there. We're just going to rewrite vi as ddt of ri, right? Derivative of position is velocity. These are exactly the same. M is constant for each particle. The particles aren't changing mass, so we can bring m into our derivative here, and that would allow us to take the derivative of this entire thing. So d dt of this right here. And we just said that this term here, miri, is m r over bar. And I can show you that here. If we multiply both sides by m, we would end up with mr equals numerator up here. That's where that came from. So this whole term is just mr over bar. So we can write that as d dt of mr over bar. And so this is p, the momentum, is equal to mv over bar, right? Because m is constant. That's the total mass of the system. We can take that out. And then we're just left with d dt of r, which is v, right? And just one more thing to note here. This means that m d dt of r is equal to mv. And we can cancel the m's here. And so we'd be left with d dt of r is equal to v. So that is v, and we'll come back to it, but we're going to write it a different way also. So just keep that in mind. So therefore, we can write the velocity of the center of mass as, so we're just taking this definition right here, p is equal to mv over bar, which we just found, and p we also said was equal to this right here. So we're just going to set those equal to each other, right? All we did was set this definition of p equal to this definition of p. Divide both sides by m here, and we'd be left with this right here. So the definition of the velocity of the center of mass is the derivative of the position vector of the center of mass, which is equal to this right here, right? And this looks really, really similar to this, right? Definitions are similar. Finally, we know acceleration is the derivative of velocity, so let's just take the derivative of this. So we're going to say the acceleration of the center of mass is equal to, mi, and then we're going to take the derivative of this v term and divide by m. M is constant. We can do the same kind of trick we did above, where we can move in mi and then take the derivative of the whole summing notation, which is what we're doing here. M is constant, that's why it's hanging out front. And we just said that this notation right here is equal to mv over bar, right? We just did that right here. So that means we're left with d dt of mv over bar over m. You can take m out of the derivative, the m's cancel, and then we're just left with d dt of v. So the acceleration of the center of mass is the derivative of the velocity of the center of mass, which is equal to this notation right here, which is that weighted average of all the accelerations for each particle divided by the total mass. So finally, in summation, these are our definitions for the location, the position vector of the center of mass, the velocity of the center of mass, and the acceleration of the center of mass. We'll be using this a lot moving forward for talking about systems of particles and in future examples. So I'll see you in the next video. Bye.